Anyway, let us continue because I was trying to call my either my mom or dad. They are in upstairs, so let's see when I can connect to them. Otherwise, we can continue. Okay. So this particular case is also gradient. So this r is again the position vector. So you just take the magnitude of that r. This is the small letter r without any vector sign, and 1 upon r is this, and this is simply x square plus y square plus z square to the power minus of 1 upon 2. So similar to what we have done before, when you take a gradient, this will be operated by this del upon del x, and del upon del y operation also will perform on that. Del upon del z operation also will perform on this, and then you just take the differentiation, simple differentiation, and this is what you get. Okay, so this is simple. Now let's see this Laplacian operator or scalar operator. It's also called the scalar operator in the sense that when you take a single del operator is a vector operator because of this vector sign here, because the resultant of this del operator operating on a scalar quantity is a vector, right? But Laplacian is a del square operator. Del square means del dot product between del operator to vector operator. When you perform a dot product, the resultant is a scalar operator. So this is like this: I cap dot I cap is 1. Therefore, del square upon del x square, you have the first operator. I dot j cap is 0. I dot k cap is 0. And now if you look at this, j dot I is 0. J dot j is 1. Therefore, del square upon del y square, and similarly del square upon del z square. Now, this also again you can perform this r, your position vector you already know. Position vector you already know, xi plus yj plus zk. So you take the magnitude like I explained before, and 1 upon r is this. You perform this del square operation. So if you perform a del square operation on this scalar quantity, and all of these are scalar quantities. So scalar operator operating on scalar quantities. So this you have to operate with this you have to operate with this and this. So it's a double derivative. So this is simply again a simple calculus. This is just a differentiation. If you differentiate it once, this is what you are going to get, and differentiate it again using a differentiation by product rules. Differentiation of product rules, you know that this is, let's say, f and g, two functions you differentiate. So differentiation of second function with the first function plus differentiation of first function, like this. So it's a differentiation of product rules. You just follow that and you will get the result. Okay, I don't want to get into that detail. Now this is another vector identity which you should always remember. Here phi is a scalar quantity, a is your vector field. So if you're going to take divergence of product of phi and a, this is how it's going to be, like that. So phi into a means phi is a scalar, a is a vector. So when you multiply scalar and a vector, you have to multiply all the components of a vector. You have to multiply all the components of a vector with a scalar. Whenever you multiply scalar with a vector, this scalar quantity will have to be multiplied to all the components of the vectors. So when you multiply to all the components of the vectors, this is what you are going to get, right? So when you take a divergence like this, I dot I is 1. So del phi a1 upon del x, j dot j is 1. del phi a2 upon del y. K dot k is 1 del phi a3 upon del z. Right. So again, a1 is now, as I said before, a1 is the coefficient of I cap. It could be a function of x, y, and z, like I already mentioned before. A2 could be a function of x, y, and z. So considering that, if you have the product of phi and a, phi is also a function of x, y, and z. So it's a product of two functions of x. So you just follow the differentiation by product rule. First, differentiate the first function, multiply with the second function, plus differentiate the second function, multiply with the first function. So differentiation by product rule, you just follow it here. This is what you're going to get. And you combine this term here. You combine this and this term over here. So what you have here is this is a product of two vectors. Here you can see that, like I explained before, if you have two vectors a, b, like this, a1 I cap plus b, sorry, a2 j cap plus a3 k cap, dot product with b1 I cap plus b2 j cap plus b3 k cap. So if you take a dot product here, what you're going to get is a1 b1 plus a2 b2 plus a3 b3. So if you have this term and this term, this term and this term, you can see that this is actually del phi upon del phi upon del y, del phi upon del z, dot product with this. So del phi upon del, this term is your gradient of phi, and this is your vector a, and over here this is if you look at this, phi as a common factor, you take it out, and this will be this operating on this vector, divergence of a. So I hope you know what it is now, because I've shown you divergence of a. So this is a vector identity which you should remember. Okay, so this is the proof of that. And this is also another vector identity which is also very like relevant in many engineering and physics calculation. So phi is a scalar quantity. So when you take a grad phi, this is a grad phi, and when you take the cal again on that grad phi, so I j k del operator is del upon del x, del upon del y, del upon del z. Cal means this term also del phi upon del x, coefficient of j cap, here in this case the second vector. Grad phi is like the second vector. In the second vector, the coefficient of j cap is del phi upon del y, and the coefficient of k cap is del phi upon del z. So you have to put it like that. And if you follow the cal formula, the cal that we have already discussed, I coefficient will be this quantity operating on this. So del square phi upon del y del z minus this quantity operating on this del square phi upon del z del y, and similarly you will get this and this. And we know that phi is a scalar quantity. In a scalar quantity, whether you differentiate first with z and then perform differentiation with y, or you first perform differentiation with y and then perform differentiation with z, it does not matter. So you will get the same result. If you interchange the order of differentiation with respect to the space variables, you get the same result. So they are identical. So they will cancel out, and similarly this cancels out, and what you're going to get is cal of a gradient of a scalar field. Any scalar quantity you take, cal of a gradient of that scalar quantity is always 0. Okay. So this is also another very important vector identity. Here A is a vector field. This is like, you can pronounce it like, this is divergence operation, and this is cal. That means divergence of cal of a vector A. Okay. So now A is a vector. This is del operator. When you perform a cal, first you calculate this cal. When you perform a cal, this is what you're going to get. Then you perform a divergence. Divergence means this del operator dot here, del operator dot product with cal of a vector. Cal of a vector is this quantity. So you put this quantity as the cal of a. So I dot I is 1, right? So this del operator operating on that, del upon del x, j dot j is 1, j, not this, not z cap, this is k cap, k cap dot k cap is 1. So I dot j, I dot k, they are 0, because this we have already discussed. You should always remember that I dot I is 1 and j dot j is 1 and k dot k is 1. However, dot product with I dot j is 0 and sorry, I dot j is 0, I dot k is 0. So because they are orthogonal vectors, I, j, and k, they are pointing along x axis, y axis, and z axis. They are orthogonal vectors. The angle between them are 90 degrees, right? So because of that, their dot product is 0. Because cos 90 is 0. We know that. So if you perform this, the first term you have del square a3 upon del x del y, and over here, del square a3 upon del y minus you have. So these two terms cancel out, and similarly this and this will cancel out, and this and this cancels out. And eventually he will find that for any vector field A, divergence of curl of the vector field is 0. So the reason here is that curl of A will measure the rotation of the vector field. If A is non-rotating vector, curl of A is 0. So it does not matter when you perform a divergence again. Okay. But if curl of a vector A is finite, that means vector A is a rotating field. But when you perform a divergence on a rotating field, then again this is 0. So the divergence of curl of A is always 0 for any vector. And this is your assignment. Take curl of vector A and see that this is equal to this quantity. So this vector identity is also very, very important. This is something you should not, you should always remember. This vector identity is very, very important. And again, this vector identity is also very important. We will often use it in physics and engineering calculation. Cái off tỏ mò, mà là tùy bông cái off. Cái mấy lâu tùy liềm này cho okay. Class cái lạc lộ đâu cái anh so. Okay. Now, this is the last topic which I plan to discuss for today, because next will be divergence theorem, that we will do it next week. Now, here, so that gradient of any scalar quantity, gradient of a scalar field is a vector perpendicular to the surface represented by this vector. If you look at this, this is a little bit vague. So this is x-axis. Let's say this is y-axis. Let's say this is z-axis. Unit vector along this axis is I cap. Unit vector along this axis is j cap. Unit vector along this axis is k cap. Okay. Now let's say we have a certain plane. Certain plane like this. Let's say we have a certain plane. And this plane intersects the z-axis at, let's say, 1, 2, 3. Let's say this is where the plane intersects the z-axis. That is at z equal to 3. Okay, it intersects the z-axis at 3. So if this is an infinite plane, that means it extends in this direction, extends in this direction up to infinity, extends in this direction up to infinity. When we have a fixed plane, the equation of this plane will be z equal to 3. Equation of this plane, equation of the plane will be z equal to 3. Why do I say that z equal to 3 is the equation of the plane? Because for every point on this plane, if you take any point on this plane, z value will be 3. Because we have a plane which is parallel to xy plane, right? It is parallel to xy plane. So from xy plane, the height of that plane is always 3. The height of the plane is always 3. So for every point on this plane, z value is always 3. So this is the equation that defines this infinite plane. So if you compare with this here, phi equal to c, that means here your phi is 3. Your phi is z, your c is 3. Right. So now if you take a grad of this, grad phi will be I del upon del x plus j del upon del y plus k del upon del z. Phi is z, right? So differentiation of z with respect to x is 0. Differentiation of z with respect to y is 0 plus k cap. Differentiation of z with respect to z is 1. So grad phi, as you can see, this is equivalent to k cap. Grad phi is equal to k cap. See, that's exactly what you can see here. K cap is a unit vector pointing along the z-axis. K cap is pointing along the z-axis, right? So as you can see, k cap is a vector perpendicular to z equal to 3 plane. K cap is a vector perpendicular to z equal to 3 plane. So this is what we are trying to prove. Here, for this particular plane, we can find that grad phi actually represents a vector which is perpendicular to the surface. Grad phi actually represents a vector perpendicular to the surface because k cap is a vector perpendicular to the surface z equal to 3. So if z equal to 3 is the equation of this surface, k cap represents the vector perpendicular to the surface, which is actually your grad phi. Yeah. Now, this is something we have discussed again before. This is x, y, and z. And if you take any point here or in the space, the position of that point is represented by position vector r. And if you move in this direction, the small changes in the point is represented by dr. So the resultant vector here is r vector plus dr vector. Similar to that, now if you represent any point on the surface as using this position vector r, if you move from one point to another point in the space in this surface, let's say this point, this is, if you move to another point on the surface, this is, let's say, your dr. Your dr vector here will be, dr vector will lie on the surface. Dr vector will lie on the surface of the plane. Okay, dr vector will lie on the surface of the plane, or dr vector will be tangent to the surface. The surface. So remember that dr vector will be tangent to the surface. All right. Now let us continue. So let's say we take r as a position vector. We already know this is the position vector of any point on the surface phi. So we, in the earlier case, for simplicity as an illustration, we have considered a flat surface. So we can actually have any kind of arbitrary surface like this. Okay, arbitrary surface. So let's say we have a surface like this, and we take dr, r vector here, be the position vector of any point on the surface, represented by this phi x, y, z equal to c is the equation of the surface. dr will be a tangent vector to the plane of the surface. So if you take a dr vector here, so if we move to another point on the surface, dr vector will be a tangent, or it will be parallel to the plane of the surface. Okay, tangent to the plane means it will be a vector which is parallel to the surface. Now Here, the equation of the surface represents that phi x, y, z is constant on the surface. Phi is constant on the surface. So since phi is a constant, any change in phi on the surface, d phi on the surface is also 0. Okay. So if you are moving from one point to another point on the surface, d phi, change in phi is 0 because phi is a constant. This is the equation of the surface. Like over here, for this infinite plane, z equal to 3 is the equation of the plane because z value is constant for every point on the surface. So if you move from one point to another point on this planar surface, z value is always 3. So that means change in z, dz, as you move from one point to another point on the surface, change in z, dz value is always 0. Similar to that, you take any arbitrary surface. It could be a curved surface, it could be a cylindrical surface, or it could be planar surface. We are just considering any general surface, which is defined by this equation phi x, y, z equal to c. And we are considering that r to be the position vector of any point on the surface. And here, like I explained before, dr will be when you move from one point on the surface to another point on the surface, the change in the position vector is your dr here, okay, which is represented like this. And as you move from one point to another point on the surface, your phi value is, change in phi is 0 because this is the equation of the surface, like we discussed here. Z equal to 3 is, z is constant on this surface. So we are considering, to represent the equation of surface, we're considering some quantity, some functions, scalar functions, which is constant. Now using partial derivative law that we did explain before, phi if is having a dependency on more than one variable, so we can write it like del phi upon del x into increment on x, del phi upon del y, how quickly phi changes with y multiplied with increment on y, and similarly this. So using the dot product rule, you can again separate out these two terms consisting of this and this. And the first term, as you see, it's a grad of phi, and the second term is, see, this is dr. Dr is tangent to the surface, or dr is on the plane. Dr is on the plane or tangent or parallel to the surface. Right. Dr is on the plane or tangent or parallel to the surface. Right, like I discussed. So if you take a dot product here, this will be magnitude of grad phi, magnitude of dr into cosine of the angle between them. So as you see, the dot product between these two vectors is 0. The dot product between these two vectors is 0 only if theta is 90. That is, the angle between dr vector and grad phi is 90 degree. All right. So that means we know that dr is a vector lying on the surface of the plane at that particular point. And then this is perpendicular with grad phi, means grad phi is perpendicular to the surface. Okay. Grad phi is perpendicular to surface. I hope you get the idea, because dr is tangent or parallel to the surface at that particular point represented by your r vector. Therefore, since the dot product between dr and grad phi is 0, that means grad phi is 90 degree, at 90 degree to the surface at that particular point represented by r vector. Right. So that's it for today. I will stop here, and I will have to split the lecture video into 2 parts, and then after that I will upload. So from tomorrow we will study divergence theorem, Gauss divergence theorem, and yeah, some proofs and all. Not tomorrow, maybe on Friday. We'll see if it's convenient to take a class in the evening. Yeah, I'll stop now.